All right, let's dive right in. Welcome to today's explainer, where we are looking at how vague everyday ideas are transformed into precise, unshakable blueprints. Have you ever stopped to wonder how a massive skyscraper, a microscopic computer chip, or honestly, even just the desk you're sitting at right now gets built exactly the way it's supposed to? Well, it absolutely doesn't happen by accident, and it certainly doesn't happen with casual conversation. It happens through the incredible, rigorous power of technical specifications. Here is our roadmap for today. We'll kick things off by comparing portraits and blueprints, then we'll decode the language of requirements and break down the 4 specification types. After that, we'll ground all of this in a quick case study on a phone case before wrapping up with tolerances in the real world. Section 1, Portrait versus Blueprint. Let's establish the ground rules. There is a stark difference between two completely different ways of writing about physical objects. Think of a technical description like a portrait. It captures what an object is, what it looks like, and how it works right now. Crucially, descriptions are written about things that already exist in the real world. But a specification? That's your blueprint. It dictates what an object absolutely must be, what it must do, or what it must withstand to be considered acceptable. Specifications are written before the object even exists. They're the strict guiding instructions for the people who are actually going to design and build the thing. And these blueprints literally dictate the world around us. They are the invisible scaffolding of the professional world. A school district isn't just ordering some nice desks. No, they specify that the desk surface shall measure no less than 24 inches wide and 18 inches deep. A software company demands that a new search function returns results within exactly 2 seconds for queries up to 500 characters. Even the roads we drive on are governed by specs, requiring the asphalt layer to have a minimum compacted thickness of exactly 3.0 inches. It's all about precise, measurable rules. Moving right along to Section 2, the language of requirements. In technical specifications, everyday words take on massive, professional, and even legal weight. The absolute, undisputed king of these words is shall. When you see shall on a spec sheet, it means the requirement is mandatory. There is zero flexibility here. The product must meet this exact condition, and if it fails to comply, the product simply does not meet the specification. It's literally the difference between a contractor getting paid or facing a massive lawsuit. Shall is an absolute guarantee. Now compare that absolute ironclad rule with our next word, should. Should represents a recommended requirement. The product ought to meet this condition, and if it doesn't, well, there better be a really good reason why. Non-compliance requires real justification here. But unlike shall, failing to meet a should requirement doesn't automatically disqualify the product. It gives engineers and designers a tiny bit of flexibility to solve problems creatively, while still keeping them strictly accountable. And finally, we have may. This one is purely optional. The designer or builder can include this feature if they want to. Maybe it adds some value or convenience without blowing up the budget, but they are absolutely not required to do it. It's left entirely to their professional discretion. Let's actually look at a before and after to see how these words totally transform a vague idea. We start with some casual language. The phone case needs to be pretty strong, water-resistant, and come in a few colors. I mean, that is absurdly vague. What exactly is pretty strong? Now, check out the professional translation. The case shall withstand a 6-foot drop onto concrete, carry an IP67 water rating, and should be available in at least 3 colors. See that? We replaced pretty strong with a hard 6-foot drop test. Water-resistant became a globally recognized testable IP67 rating. We went from casual chatter to rigid, testable criteria. Which brings us to the single most important question you have to ask yourself for every single requirement you write. How would I prove this is true? A specification is completely useless if you can't test it. If you say the screen shall be bright enough, how do you test bright enough? You literally can't. But if you say the screen shall produce a minimum luminance of 500 nits, you just put a light meter on it and prove it immediately. Testability is the gold standard here.
All right, Section 3, the 4 specification types.
Any complete professional spec document leans heavily on 4 distinct pillars. First up, performance specifications. This defines what the product actually has to do, like making sure a printer pumps out a minimum of 30 pages per minute. Second, material specifications. This dictates exactly what it's made of, like specifying 6061 T6 aluminum alloy for a bicycle frame. Third, dimensional specifications, which lock down the exact size and shape right down to the decimal point, like 12 by 8 by 3.5 inches. And fourth, quality specifications. These define the rigorous standards for appearance and finish, for example, dictating that there can be 0 visible brush marks when viewed from 3 feet away. A truly masterful spec sheet weaves all four of these categories together flawlessly.
Section 4. Case study, the phone case. Let's look at a complete specification.
Let's see how all these abstract rules snap together to build something tangible, like the phone case you probably have in your pocket right now. Looking at this matrix, we've combined legal terms with precise metrics. Under dimensional, the case shall have a snug fit, allowing a maximum of just 0.5 millimeters of movement. Under material, it shall be molded from TPU with a short A hardness of exactly 85 to 95, and it shall be BPA-free. Performance dictates it shall withstand a 4-foot drop according to military standard 810G. Every single row tells the manufacturer exactly what to build and exactly how we're going to test it to make sure they actually did it right. There's no room for dangerous misinterpretations.
Which brings us to our final section, Section 5, Tolerances in the Real World.
Because here's the messy reality of manufacturing. Absolute perfection is physically impossible. You ask a machine for exactly 10.0 inches, you're going to get 10.01 or maybe 9.99 inches, and that's where tolerance comes into play. Tolerance defines the acceptable range of variation in a manufactured part. You'll see it written as a plus or minus value right after the target measurement. It's basically an engineering acknowledgement that every single manufactured item on planet Earth has built-in wiggle room.
Take a look at this number, plus or minus 0.5 millimeters. That's a relatively loose tolerance. It represents the acceptable variation for something simple, like the diameter of a plastic pen cap. It perfectly fits an everyday, low-stakes item. If your pen cap is half a millimeter wider or narrower, it doesn't matter. It's still going to snap onto the pen just fine. The stakes are low, so the tolerance can afford to be loose.
But then, contrast that basic pen cap with this intense number, plus or minus 0.001 inches. This represents the tolerance for a jet engine turbine blade. When you're at 30,000 feet and that blade is spinning at thousands of revolutions per minute, even a microscopic variation could be completely catastrophic. The context always dictates the level of precision you need. And that brings up a massive reality check when it comes to engineering and economics. Tighter tolerances cost way more money and slow down production significantly. It is a classic, very costly rookie mistake to overspecify your tolerances just to make your document sound more professional. Like, if you're building a simple wooden bookshelf that's 36 inches wide, specifying a tolerance of 0.01 inches is just absurd. It would multiply the cost of that bookshelf exponentially without actually improving how it holds books in any meaningful way. So here is the golden rule of manufacturing you should take away from this explainer. What is the loosest tolerance that still meets the functional need? It's a profound shift in how we view precision, isn't it? It's not about blindly chasing absolute perfection. It's about achieving the exact right amount of precision required for the job without wasting a single penny or a single second of time. So the next time you hold any physical object, your phone, a pen, or even the steering wheel of your car, ask yourself, what are the invisible rules, the unshakable blueprints, and the hidden tolerances that are actively holding your reality together?